Kia ora, welcome back. Welcome to week 4, lecture 2. Now, there was a lot of theory last time, so today we're going to do something a bit more immediately practical. We're actually going to solve some second order differential equations. Now, the general higher order linear equation that we looked at last week, you can't always get an analytical formula for the solution. It depends on those coefficients. And the simplest case is when those coefficients are just constants. So here we're going to look at the constant coefficient equation. Now this title here looks a bit complicated, right? It's this enormous noun phrase. So we're studying equations. That's the noun. What kind of equations are they? They're differential equations. Oh, actually they're ordinary differential equations. Actually they're special ones. They're second order ordinary differential equations. And actually we're not going to look at the general second order ordinary differential equation. We're only going to do the linear ones. Oh, actually, no, we're not doing the all linear ones. We're just doing the constant coefficient linear ones. And actually, I'm also going to make the right-hand side 0. So we're going to look at homogeneous, constant coefficient, linear, second order, ordinary differential equation. So it's a noun phrase with 1, 2, 3, 4, 5, 6, 7, 8 adjectives that qualify the noun. And we're not even up to very complicated stuff yet, so there we go. There's science for you. Okay, so we know it's second order. That means I need to find a fundamental solution set with 2 solutions in it. And there's this absolute genius thing you can do, which is guess the solution. And I'm going to guess that the solution would be an exponential. Why is that a good guess? Well, remember that equation dy dx equals 2y that we started with in week 1? The solution turned out to be e to the 2x. It was an exponential. And this equation looks a bit like that, so I'm going to try that. Differentiate it, and m is a constant to be determined. I need to differentiate that to substitute it into the equation. That gives me m e to the mx. Y double prime is m squared e to the mx. Substitute into the equation, I get a m squared e to the mx plus b m e to the mx plus cy plus c e to the mx equals 0. Now it doesn't. I'm not solving for x here. This has to equal 0 for all x. Let's simplify that a bit. I've got a common factor e to the mx. And this term here, e to the mx, that is never equal to 0. So I can divide by e to the mx and get am squared plus bm plus c equal to 0. Now that's an equation for m. So if that equation has a solution, I've found a value of the constant m, which gives me solutions of the equation. This is called the indicial equation. And notice that the differential equation was ay double prime plus by prime plus cy equals 0. And the indicial equation is very similar. It's am squared plus bm plus c equals 0. So you can see why this guess worked. It was because when you take any exponential, e to the 2x, e to the 3x, any exponential like that, and differentiate them, you've still got a function of the same type. And you can see why this wouldn't work so well if there were some functions of x in there. For example, if I had an x in that first term, suddenly it wouldn't work anymore. Now, this is a quadratic equation for m, so it always has 2 solutions. That's the fundamental theorem of arithmetic. If I allow complex solutions, this will always have 2 roots. You might have a repeated root, but we'll handle that case. So we know we wanted 2 solutions, so we appear to be done. If I found 2 values of m, say 2 and 3, and e to the 2x and e to the 3x were both solutions, I could very easily show that they were linearly independent. I'd have found a fundamental solution set, I'd be done. So it's very powerful. So we need to consider different cases now, because there's 3 different cases of a quadratic. You may have 2 real roots. I should say 2 real distinct roots, namely not equal to each other. So let's call them m1 and m2. Then e to the m1x and e to the m2x are linearly independent on the real line. I'll leave that to you to show why that is the case. It should be an e to the 2. So that means I have the general solution. Constant times e to the m1x plus a constant times e to the m2x, and I'm done. That's the power of that general theory that we did last time. We've solved the equation. Now, you may notice that nothing I did here was really special to the fact that I was a second order equation. And this happens a lot. Once you've gone to second order, you're already into the general case, basically. So if I had a higher order constant coefficient linear equation, say with 4th derivatives, I could still substitute an exponential. Instead of a quadratic, I'd get a higher degree polynomial. It would have n roots. I could solve the nth order constant coefficient equation in just the same way. So this is really just to make the writing easier to do the second order case. Okay, so 2 real distinct roots, when the roots are different numbers, you're done. Now we'll do the case of 2 equal roots. Now remember what the roots are. The roots are going to be minus b plus a minus root b squared minus 4ac over 2a. So the roots will be equal when b squared minus 4ac is equal to 0. And in that case, the roots will both be equal to minus b over 2a. And now there's a problem, because I don't have 2 linearly independent solutions. I have e to the mx, but my second solution is also e to the mx. So I'm just going to write down the answer here. That would mean we'd need to look for a second linearly independent solution. C1 e to the mx, well, I'll just call m for that root, plus C2. So the second linearly independent solution turns out to be x e to the mx. So I'll leave that to you as an exercise. Check that this second one is in fact a solution to the differential equation in this case. You can also check that it's linearly independent, so this is the general solution. Now, you might not find that very satisfying, because we once again just seem to be guessing a formula for the solution. But in this case, that's not quite the case. There is a way of finding the second solution when you know one solution. We can look at that later. Okay, so the 2 equal roots case is easy as well. Now we have the case of complex roots. So this is when b squared minus 4ac is less than 0. So let's call the roots m. Let's call them alpha plus or minus I beta. We just work out whatever the roots are, and we call the real part alpha, and we call the imaginary part beta, and we know that they will form a complex conjugate pair. What's the lesson from complex numbers that we did in 102 algebra? Don't be afraid of square roots of negative numbers. Don't be afraid of complex numbers. All the rules work just fine, and we'll see that here too. So we get a solution. Y equals e to the mx. That is e to the, let's just do one of them. That is e to the alpha x, e to the I beta x. Now this looks familiar. Do you remember Euler's magic formula? E to the I theta is cos theta plus I sine theta. That's how you turn complex exponentials back into real imaginary form. So that means my solution now looks like e to the alpha x times cos beta x plus I sine beta x. So the complex solutions are very interesting. The real part of the root of the intercell equation tells you the rate of exponential growth or decay. So alpha, if alpha is positive, you have exponential growth. If alpha is negative, you have exponential decay. And the imaginary part tells you the frequency of oscillations. So for example, these solutions are going to look like, let's say alpha was 1. So my envelope would be like that. And my solutions are going to oscillate with frequency beta going up and down between this exponential envelope. So that is fine. That is the solution, and then from the other root I get the other solution, and they are linearly independent. But you may want to write the solution in real form. So let's call this one y1, and then the second solution we'll call it y2. That was with a negative b, so we'll get e to the alpha x cos beta x minus I sine beta x. So compare this one and this one. They're complex conjugates of one another. How can I get rid of that I? Well, if I add those two together, the i's will cancel. That will give me 2e to the alpha x cos beta x. And we know that you are allowed to add solutions together because of the superposition principle. So the general solution is going to be, in real form, would be c1 e to the alpha x cos beta x. That's the one I get by adding those two solutions and dividing by 2. And if I subtract them and divide by I get the sine beta x. So there we go.